Our next problem is also straightforward conservation of momentum in one dimension. Um, the thing to note is that this is exploding into pieces at the peak of its trajectory. So it was launched vertically, and it's exploding at the peak of its trajectory. This means Vy equals 0, and this means Vx equals 0. So the explosion happens when the velocity vector is 0. So what do I have here picture-wise? So I've got a firecracker that starts off with two pieces. There is a big piece, a blue piece, that is 72 grams. There is a big piece over, or a smaller piece over here, the one I'm drawing in orange. It's the rest, so it is 28 grams. We'll call these masses M1 and M2. And then after the explosion, which makes that noise, the 72 gram piece is moving to the left at 20 meters per second, which I'll label V1 final. And the other piece is going to be projected to the right. V2 final equals question mark. So this is just conservation of momentum in one dimension. So here I've got the two of them are together and not moving in the beginning. So if initial momentum equals final momentum, 0 equals M1 V1 final. And I'll write this with a minus sign because I'm letting V1F be the magnitude. So here, I'm just going to make a label. V1F is the magnitude 20 meters per second. The minus sign here represents the direction. Plus M2 V2F. So doing a little bit of algebra, V2F equals V1F times M1 over M2. Let's see, so the pieces are 72 grams and 28 grams. The velocity that one is being projected at is 20 meters per second. So if I put these numbers into the Google machine, I have 20 meters per second. Whoops, typing into the wrong window. 20 meters per second times 72 grams over 28 grams gives me 51.4 meters per second. And that's going to go rightward. So another very straightforward conservation of momentum in one dimension problem.